So one of the nice things about molar solubility is that the calculation of S or X in these equations can be really easy uh, in terms of not having to solve quadratic equations if you don't have any starting material around. So let's go ahead and look to see what the solubility product expression would be for the dissolving of calcium hydroxide. So we would write a reaction that says CaOH2 solid is in equilibrium, right, with Ca2 plus 2OH minus, and so that's what we put at the top of our ice table. It's always for the dissolving of the solid again, and you can get the coefficients from reactions from the subscripts that are down here. So there's the 1 for the calcium, right, and the 2 for the hydroxide. If we start with 0 concentrations for both, we know the equilibrium has to be towards the right, and so we're going to use S and S here, but then again, just like if it had been X, you would have put 2S or 2X there, and so the equilibrium line becomes S and then 2S. Now, the expression for this, KSP, is going to be equal to the concentration of calcium, right, times the concentration of hydroxide squared. And now I can substitute in sub in S expressions, okay? Go right into here. So now what I have is KSP is equal to, sorry, the change of setting, S times, right, and then hydroxide's 2S squared. So this will become S times 4S squared, so that's 4S cubed. And then you can see how I can solve for a solubility product by setting 4S cubed equal to KSP. I'll go ahead and keep it as KSP because it's shorter to write. And I'll divide both sides by 4, and then I'll take the cube root of it like this. And so that's going to be plugging in, right, this value here. That ends up being 0.01537 molar. Okay? So this is how you would calculate a molar solubility. You go ahead and figure out what the expressions are for S's in your concentration. You write your solubility product expression over here. You plug in the S's. You solve it down to a single term of S, and then again you solve for the value of S by isolating S in the equation. Anyways, pretty straightforward. So we're going to go ahead and look at a couple of others so you can get some practice. So when we practice, what we're going to do is actually practice to answer this question. Does larger KSP always mean more soluble? This is actually what I was getting to back here, that the amount of material that dissolves here depends on the solubility product, but it also depends on the solubility product expression, that is these values over here. So I've used these same compounds over here. So we already have the solubility product expressions. But before I write them out, because I'm not going to do an ice table every time for those, that's kind of a waste of time for these ones with zero concentration. Just make note of the idea that the expression for calcium is S, right? The expression for hydroxide ended up being 2S, so it's just the stoichiometric coefficient in the solubility product expression and as the exponent for that term. So for example, let's do calcium phosphate. Barium carbonate is pretty straightforward, and when I do that, I'll do that one in a second. But calcium phosphate would be KSP. So to do this one, right, what you have to think about is what the ice table looks like. So I have calcium, and there's a 3 here, right? So I'm going to have a 3S in here. And then in the solubility product expression, that would be cubed. And for phosphate, there's a 2, right? And so that's going to be 2s. That's this 2 here. And then the whole thing will be squared. So we'd have to do the math to straighten that all out. But for barium carbonate, it would just be 1 and 1. So I didn't want to do this one too early because you get some misconceptions about what it should be for all of them if you do this one first. But they're just S and S. But don't forget, if you have a coefficient in the equilibrium that is coming from this subscript, it needs to be what the value that's in here. So now we have to do the math of simplifying these things out. This becomes S squared. This one becomes 3 cubed times S cubed, right? So that's 3, 9, 27. S cubed times, and then 4S squared. And then what you need to do is sort of, again, do the algebra. You'll end up with 108 S to the 5th power, like that. Now, for the iron hydroxide, if you pause, you can check yourself, but I'm going to go ahead and work it out. So that's the same as what you saw before for barium hydroxide, right? And for calcium hydroxide. I think I did barium hydroxide, or barium, I thought I did a barium hydroxide somewhere, but maybe I didn't. Anyways, the idea is this, though. What a lot of people get used to doing after fashion is looking at the expression as a metal, right? And 2x is attached to it, and those always have the same form for the solubility product expression. So in fact, that's why I originally wrote this one this way, is so that if you start thinking about it in terms of ions and numbers of each ion, the solubility product expression is always the same, provided that the equations for the dissolving of the solid have the same form. That means they have the same numbers in terms of stoichiometric coefficients. All right, so from each one of these, we can calculate an S. And so when I do the solution for S for barium carbonate, what I end up with is 5 times 10. Sorry, it's 5.1. I had my math wrong and I stopped and changed it. So it ends up being 5.1 times 10 to the minus 5th. This is for the solution of barium carbonate. For calcium phosphate, that ends up being 1.14 if you're doing the calculation with me, times 10 to the minus 7. And then iron hydroxide ends up being, so this is just solving for S, iron hydroxide ends up being 2.3 times 10 to the minus third, like this. So here's the deal, like, which one is the most soluble? It turns out this is the most soluble. And the reason is because of the form that the solubility product takes versus the barium carbonate. Okay, so the most even though the KSP is bigger for barium carbonate versus iron hydroxide, you can dissolve more iron hydroxide simply because in the form of the equation you end up taking the cube root, which takes this expression and makes it bigger, right, than what you get for barium carbonate. The least soluble turns out still to be calcium phosphate. You might have predicted that it would be the least soluble. But, again, it's not that different in comparison to the other ones, considering how much smaller it was. And simply, that's because you're taking the 5th root of the solubility product at some point, divided by 108. So, the moral of the story is there's two, actually. One, if the forms of the ions are different, the ionic compounds are different, that is, they give different solubility product expressions, right, in terms of S, then you have to calculate molar solubility to figure out which one's most soluble. On the other hand, if I'm straight up comparing barium carbonate versus, let's say, barium sulfate, because these are MX forms like this, all I need to do is look at the solubility product. So to compare like structured ionic compounds, compare KSP. But if they're dissimilar in terms of their structure, then you actually have to go through and calculate molar solubility for each one.